Hello students, last time in first video of assignment 4.6 we had torque acting on a current carrying coil placed in external magnetic field. Now we will have quick revision of what we got last time, and then we will see what is galvanometer, on which principle it works, and what is the construction of galvanometer. So let us first have a look at the last time's topic. So in last time assignment in video session, we had a rectangular coil, and as shown here, we had four forces acting: F1, F3, F2, and F4. And then we saw that F1 is the force acting on wire PQ, and it can be given as I L B J cap. It was in vertically upward direction. F3, if we look at, F3 is minus ILB J cap. So we saw last time that these two are equal and opposite. Moreover, they have same line of action. If you look at the two, they are on the same line, and hence the torque due to the two is also zero, not only force. So in short, you can say that F1 and F3 they have no role to play for any rotation or movement of the coil. But then look at F2. What is F2? So if length of the wire is small b, if it is denoted by small b, then you can say that F2 is I B B K cap. Okay, and then F4 is minus I B B K cap. So again, the resultant force of this two is zero, but as they have different lines of action, F2 is acting somewhere here and F4 has some other line of action. So the two have some perpendicular distance between them. They have some distance between them. So the resultant force of this two, F2, F4 is zero, torque is not zero. And then we did calculate that torque can be determined by taking force into perpendicular distance of force, and perpendicular distance is L sine theta. And then ultimately what we had was torque is equal to NIAB sine theta. So what is N? If you take torque to be NIAB sine theta, what is N? N is number of turns. What is I? Current passing through the coil. What is A? Area of the coil. And what is B? Applied magnetic field. Then what is this theta? Okay, in this figure theta is not shown. Let us try to understand what is theta. So suppose if the coil is suspended like this, then A is the area vector of this coil. So it may be somewhere here. Area vector is always perpendicular to the surface. So let this be area vector. And now if I say that this is north pole, this is south pole of the magnet, then this is the B direction. And angle between these two is called theta. So now what happens? When you have coil rotated because of the current, there are different situations possible. So consider that coil is in this orientation. Consider another situation. Now look at the difference between these two situations. If I consider it as figure 1 and the next one is figure 2, what is the angle in case of first figure? So in this case, the area vector for the coil is coming out. Dot is indicating that area vector is coming out. And look at the B direction. B is going like this. So what is the angle between A and B? So angle between A and B is 90 degree, and then we can say that torque in this case is NIAB sine 90, that is 1, so simply NIAB. But that is not the case here. In second figure, area vector is along the direction of B, and then what is the angle between A and B? So now angle between A and B is 0 degree, and then if I look at the formula NIAB sine 0. What is the torque? 0. So from this situation, when we pass current, suppose if the coil arrives at this situation, what will happen then? Once it comes to this situation as shown in figure 2, there will not be any torque acting on the coil according to this equation. Torque acting will be 0, and then even if you switch off the current, coil will remain there. Even if you increase current, coil will not rotate. Okay. So once you have this situation shown in figure 2, the torque will be 0, and then the coil or rotation is independent of current, which is not desirable situation. What we expect in galvanometer is that as we increase current, deflection should increase. As we decrease current, deflection should decrease. Galvanometer is a current sensitive device. It senses current, it detects current, right? And this particular situation is the hindrance, this situation. So what to do? So to get out of this problem, the idea given was like this. Use magnet with curved surface. Say this is top view. So here if I have my coil, say this is the coil, and then this is the area vector. So look at the nature of magnetic field lines. Magnetic field lines, if left side is north, right side is south, magnetic field lines would be like this. And so at any orientation of the coil, you will have some field lines which are always at 90 degree. And this type of magnetic field is called radial magnetic field. And for radial magnetic field, you can always consider that theta is 90, and hence torque is considered as NIAB. Okay, now as mentioned last time, this NIA is magnetic dipole moment of the coil, and sometime you may also say torque to be MB. What is M? Magnetic dipole moment. It is nothing but NIA. So in a real-time situation, we have two differences as compared to this figure. First difference is you don't have flat faces of these poles, north and south pole. You have curves shape of the poles as shown here. Second difference is in this coil, inside the coil, soft iron is placed. What is the role of soft iron? Soft iron grabs magnetic field line. So if some field line is passing nearby the soft iron, it will attract it and it will allow it to pass through itself. So soft iron will help producing this type of field, and what it is called radial magnetic field. So now one problem is solved, that if you have radial magnetic field, you will have always torque produced. You increase current, decrease current, torque is NIAB. So I can say that torque is proportional to I, N constant, A constant, B constant. So this is the desirable situation. Now the second problem is that we expect that when current is 0, the pointer, the indicator should go back to the original situation. So normally, if I consider this as the dial of galvanometer, When you connect positive and negative terminal, normally at the center you have 0, and on one side you have 30 or 40 or 50 mark, other side also same. So the pointer, when not connected, pointer is at 0 mark. Okay, and when you allow the current to pass in one direction, it will show some deflection. If the polarity here is reversed, the deflection shown will be in opposite direction. And how much is the deflection? Whether the pointer will be here or here or here is decided by how much current and in which direction. But then the other thing we expect is the moment current becomes 0, we expect the pointer to go back to 0. Now, when you pass current, suppose if the deflection is say up to this, say here, needle is here. Why needle is at the mark of say 20, suppose here you have 20 marks. So who got it there? Current. But when you switch off the current, who will get this needle back? So you need some torque which can get it back. This is called deflecting torque. This torque is deflecting torque. It is responsible for showing you reading. But then who will get the marker or needle back? So you need some restoring torque. So in galvanometer, what happens is once you have a coil, suppose this is my coil, then it is pivoted. It is kept on some support in such a way that it can rotate. Okay, and here you have spring. So, and then as discussed earlier, you have north pole and south pole in this concave manner, okay, on both sides. So if this is north pole, this is south pole, what is this? These are the pivots on which our coil, this is coil, it is pivoted, and then inside you have soft iron. What is soft iron? Soft iron is a type of iron which is more affinity, you may say, to magnetic field lines. So whichever field lines are coming out from this north pole and entering south pole, soft iron will attract those field lines and it will let it pass through. So ultimately you will have more radial magnetic field. And this springs will get the pointer back. Where is pointer? So here you will have the dial, okay, and these are the marks, and here we keep our pointer on this. So as this coil rotates, the pointer will show deflection, and when the current stops, this marker, sorry, this springs will get the pointer back. So here you have springs. So now we are talking about two torques simultaneously. One torque is NIAB and other torque is K phi. What is this called? It is called deflecting torque. And what is this called? It is called restoring torque. So we may choose to denote NIAB with tau D and K phi with tau R. Now what is phi here? Phi is the deflection produced in the coil, and what is K? K is the characteristic of the spring. It is called spring constant. So in equilibrium condition, I can say that the torque due to spring restoring torque is equal to torque due to current deflecting torque, and then I have K phi is equal to NIAB. So what is phi? What is the deflection equal to? I can write it as NAB by K into I. Why the four quantities are kept in bracket? Because they are constant quantities, and then I can say that phi, that is deflection, is proportional to current. This is the working principle of galvanometer, that deflection is directly proportional to the current passing through it. You make current zero in this, and deflection will be zero. So that is what we expected earlier, and this is what we are supposed to know in galvanometer, about the galvanometer. Now there are two quantities which we need to know about the galvanometer. One is current capacity. Now, as the name itself suggests, that if this is the scale of galvanometer, and here if I have 0, here if I have 30, then how much current I need? If I want my pointer to go from 0 to 30, how much current I need? Suppose if I need zero point 0.5 ampere, then 0.5 ampere is called current capacity. So what do you mean by current capacity? Current capacity means the current required to get full scale deflection. So unit of current capacity is ampere. How much current you need to get full scale deflection? In this case it is half ampere, so half ampere is current capacity. The second parameter we should be knowing about galvanometer is current sensitivity. Current sensitivity is a quantity which shows us how much sensitive our galvanometer is. Now, how do you determine how much sensitive it is? So again, consider galvanometer, and then initially if you have your pointer at 0, suppose this is where my pointer is initially, then how much current I need to take this pointer here, say on mark of 1. So it is the deflection occurred by the given current, or deflection per unit current. So you pass little current, and how much deflection you are getting, that is called current sensitivity. So should the galvanometer have more capacity or more sensitivity? It depends on your need. The one who is more sensitive will show full scale deflection with very little current. Okay, the one which has very high current capacity will take too large current to show deflection of 1 unit. So it is difficult to satisfy both criteria. The one which is sensitive will not have much capacity. The one which is having capacity will not have much sensitivity. So this is all we should be knowing about galvanometer. Let us have a quick look at the question answer part. Explain construction of moving coil galvanometer. So galvanometer is a device used to detect small electric currents in the circuit. Now in many books you will see that galvanometer is used to measure current. It can be used to measure current, but for that you will have to do one process of calibration. It's true that more the current, more the deflection. If you change direction of current, galvanometer can sense it. But if galvanometer is indicating 20 on its scale, it doesn't mean it is 20 ampere. For that, you will have to calibrate its scale. So you can measure current with galvanometer, but there is one calibration procedure which you will have to undergo before using it as current measuring device. We'll address it in next assignment. But for now, we will consider galvanometer as current sensing device. In galvanometer, a coil of insulated wire is wound on a frame with soft iron core. As I mentioned earlier, uh, you can have coil without anything inside, but if you take soft iron, it will grab more magnetic field lines, and then the theta value, you are getting more magnetic flux. So what is the effect of flux? Torque is NIAB. Okay, which torque it is? Deflecting torque. And then the other torque, restoring torque, is K phi. So if I compare the two, K phi is equal to NIAB, and now if I make phi by I subject of formula, what do I get? Phi by I is NAB by K. And what is phi by I? It is current sensitivity. B in the numerator, sorry, B in the numerator indicates that if B, magnetic field is more, current sensitivity is more. And soft iron is helping us achieving that. If you want to increase current sensitivity, you will have to focus on this. N should be more, A should be more, K should be less. Spring should be soft to increase current sensitivity. This coil is pivoted between two pivots with negligible friction through springs and then placed between two magnetic poles. So these are the pivots, this one and here. And this thin wire kind of thing, it may be some wire or it may be spring. The purpose is to get this thing pointed back when current is stopped. In the core of coil, soft iron cylinder is placed. The soft iron core helps producing radial magnetic flux, and it also helps increasing current sensitivity. A pointer is fixed on coil so that when current is passed through the coil, deflection is produced, which can be noticed, and you can check it on this scale. So that is all about the construction part of galvanometer. Now let us look at the mathematical part, principle and working. So as explained earlier, torque on the coil is given as NIAB sine theta. But to make it independent of this quantity, theta, we use concave shaped magnetic poles and we use soft iron core. And then what we achieve is this NIAB. Because of the radial magnetic field, sin theta is always 0 and torque becomes NIAB. And how to achieve radial magnetic field? Two ways. Use this shape of magnetic poles and secondly, use soft iron in the core of coil. So with those two, torque becomes NIAB. And this torque is called deflecting torque. And then you have one more torque, K phi. From where do we get it? Restoring torque is produced by the spring. And K is spring constant, phi is the deflection produced in the coil. And then in equilibrium, we can compare the two with little bit of mass, you get this. And this is the principle. This is the principle of moving coil galvanometer, that deflection is always proportional to current. And then lastly, these two quantities, current capacity and current sensitivity. So what is current capacity? Current capacity of a galvanometer is defined as current required to obtain full-scale deflection. Current sensitivity on the other hand is defined as the deflection produced per unit current in the galvanometer. And unit is per ampere, actually division per ampere. So that is all we should be knowing about galvanometer. I hope you understood it. Thank you.